Hello everyone, our topic for the final project is time series Scene Rate Market Prediction, which is a computation from Cargo. And in this task, we dive into the development of a predictive model based on real-world data sourced from live production trading systems. This dataset provides a rare and valuable window into the complexities and dynamic nature of financial markets, capturing the daily challenges faced in successful trading. And the dataset contains real-world market data derived from production systems. Each data point is composed of 79 features and 8 responders. Responder 6 was regarded as our prediction target, and the missing data is filled with the mean value from the entire dataset. Moreover, it is worth noting that since online testing is not available for this computation, we manually select the data from the last partition of the dataset as our testing set, and all the remainings as the training set. All models were trained and tested on the same subsets. Detailed description of the dataset is listed in this table, and the input size of each data point is 79, and the output size is 1, which is the responder 6, and the total number of training samples is 28.4 million, and the total number of testing samples is 6.27 million. And also, we did a little analysis on the dataset before we start training our models. Figure 1 is the time variance of the target responder 6. It's showing strong temporal patterns. And Figure 2 is the correlation heat map between different features. Now let me introduce our first model, which is a neural network plus XGBoost model. And in this model, we developed a neural network with 3 hidden layers ahead of XGBoost core to pre-process and consolidate the features. The output of the last hidden layer with 32 outputs is treated as the extracted features and will be fed into our XGBoost model as an input. And the detailed parameters and configurations is listed in this table. We hope the neural network can help us extract more useful information for our training with XGBoost. However, we did not consider the temporal patterns of the data in this model. We just use features from current step to make our prediction, which leads to an unsatisfactory performance on the testing set. And this also illustrates the importance of temporal structure when we are dealing with the time series data. Now let me pass to Fanghan to introduce her LSTM model for this task.
Okay, let me introduce the second model. In this model, we employed a long short-term memory neural network, a type of recurrent neural network particularly effective in modeling sequential and time series data. LSTM networks are designed to remember long-term dependencies and are widely used in applications such as forecasting, natural language processing, and anomaly detection. The architecture consists of 2 stacked LSTM layers to enhance the model's capacity to capture complex temporal patterns. The output from the second LSTM layer is fed into a fully connected linear layer to generate the final prediction. Parameters and configurations are detailed on the right. Okay, then go next.
Transformer architecture has become one of the most powerful and widely used models in machine learning, particularly in natural language processing. Given its strong ability to model sequential data, we have explored the application of a transform model for our time series regression task. For this task, we employed an input-only architecture, as the objective is to predict a continuous target variable rather than generate sequences. The model takes in a sequence of time series data, with each time step represented by 82 input features, comprising 79 features along with 3 additional identifiers. To effectively capture temporal dependencies, the input data was reshaped into sequences of length of 10, enabling the model to learn patterns over time. Positional embeddings were also added to the input to retain information about the order of the time steps, which is crucial for sequence modeling in transformers. The transformers self-attention mechanism allow it to capture long-range dependencies within the time series, making it a suitable choice for these regression problems. And other hyperparameters are also listed on the right. Next is our last model.
Yes, last but not least, we develop a time series XGBoost model, which means to fit in time series data into the XGBoost model. Specifically, we first let the dataset underwent principal component analysis, namely PCA. Specifically, the dataset was transformed into a new feature space with 10 principal components. Then, to incorporate temporal information, time series data with a window size of 20 steps was used as input into the model, enabling the XGBoost model to capture sequential patterns in the data. As for the model, a learning rate of 1/10 was chosen, while other parameters were left at their default values, allowing the model to utilize the built-in optimizations and reasonable default settings provided by the XGBoost library. Next page, please. To comprehensively assess the performance of each model, we compare them with numeric experiments. The experiment results is shown on the table. The LSTM and the neural network plus XGBoost models failed to achieve satisfactory performance on either the training or testing sets. While the transformer is very well during training, it is not good on testing due to overfitting. However, the time series XGBoost model demonstrated robust performance across both training and testing sets.
So from the experiment result, we have some findings. First is the data per process is important. For data with high dimensional features, some techniques like PCA can really help. And the next is the temporal structure is crucial for this task. The model with superior performance took sequence information into account, showing that time and order significantly influence the target variables, likely reflecting the real-world trading behavior, where past patterns affect future outcomes. A third is transformer models are powerful but not universally optimal. Despite their success in large-scale language models and time series tasks, transformers still suffer from overfitting problems and require careful tuning and sufficient data to perform well. And the least XGBoost remains highly competitive in this task, especially when handling large feature sets efficiently, and its lower tendency to overfit makes it a strong candidate for time series regression tasks. And that's all for our presentation. Thank you.